大家好, good afternoon, everyone. Welcome to the mini course of probability. So let me introduce you the speaker, Nikolaos Zygouras from University of Warwick in the UK. And so he's going to stay here for a month. He just arrived a few days ago, and he's going to stay till the last day of April. So, and he has his office just on this floor. So if you have questions later for the lectures, you're more than welcome to go and talk to him. So it's a series of 4 lectures. Today is the first one, and the second one will be on next Tuesday, and then again will be on Wednesday. So only the second one will be on Tuesday, and all the other lectures will be on Wednesday. The same time, same place. So he's going to tell us about stochastic heat flow, and he will start with something more elementary, with Lindeberg principle, and so on. So let me, let's welcome Nikolaos for the talk.
Thank you. Okay, thanks a lot, everybody. Is it too loud? Is it okay? Like this is okay. Well, it's once again a great pleasure to be in Taipei. It's becoming almost second home, and to see all good friends here and new faces that I hope to become friends with. So I would like to give lectures which will have a graduation, meaning that we'll start with something advanced undergraduate or master's, and then eventually we'll go to some research topics. So the title of the series was Jhih-Huang didn't remember, was from Lindeberg principles to stochastic SPDEs. So let me start by showing you a few pictures, which will be eventually will be shading off, but also kind of visualizing probability and what is randomness, what are fluctuations. Things that we will try to formalize through developing some techniques. So white noise. So I don't know who knows what white noise is. I would like also to measure. So who knows what white noise is? Come on, at least some people know, please. So let's okay, but that's good. So who knows what is who has the concept of family of independent identically distributed random variables? So, no? Okay. I'm asking this question just to know how to pitch also my lectures, because my goal is to keep all of you to the end. So if I lose you today to next time, it will not be good. So I would like to know, I mean, because I know there are many undergraduates also here. My goal actually is to speak also mostly to the graduates, well, the undergraduates, than to the graduates and to the researchers. Okay, so so let me ask again the question: who knows who has heard the concept of a family of independent identically distributed random variables? Please, don't be shy. Hands up. Okay, good. Okay, so in maybe not in the first course of probability, but in the second course of probability, we start talking about family of independent random variables. And so the simplest example is that you flip a coin. Okay, you flip the coin one time, and you ask what's the probability that this is heads or tails, and then you flip the coin the second time, what's the probability to be heads or tails, and then you flip the coin the third time, what's the probability to be heads and tails, and flipping the coin from one time to another, they're independent. Flipping the coin the first time will not tell you how much more likely is for the coin to turn heads in the second time. So maybe now this is a bit too basic. So let me ask again, who has heard the concept of what is a family of independent random variables? I think by now everybody should have heard it because I just said it. So, but if you don't, then I'll keep going. So please keep guiding me. Okay. So, and this is a very important because in nature, particles moving around, but particles move somehow independently. But then you have a huge number of particles. And then, even though each particle does something on its own, not communicating to the others, really, eventually all this independent randomness creates some collective phenomena. So it's very important to understand how to manage functionals of many independent random variables and how these lead to kind of a global macroscopic phenomenon. So the example I told about flipping a coin 1, 2 times and so on was a two-dimensional family of random variables. But now, if you look at the space, you have particles moving independently in three-dimensional space, right? Or you can look at the plane, and something happens at every location of the plane, which is independent of the other. So white noise actually is a continuum analog of the notion of a family of independent random variables, independent identically distributed random variables. So, and this is a visualization of the continuous notion of the independent random variables. So if you want to see how independent random variables look like, you look at this picture. So this is kind of the projection. So if you look at this surface from top, and at every point of the surface, so something happens. So you have a surface which takes independent value here than it's any other neighbor, the continuum neighbor. But in order to make a meaningful object in the continuous, when you start collectively scaling this microscopic behavior to a macroscopic behavior, then the models start becoming singular. So this is a very rough, right? So you think that the white noise is everywhere in the space, you have plus infinity. You have something that takes plus or minus infinity in a random way. And that's why you see this object here. And if you look at it from the top, you see this picture here, which I think maybe and Jhih-Huang have seen in their black and white TVs. When the TVs were not working, the connections were not good, and then instead of seeing a nice high definition picture, you see listen to this noise. Okay. So things were happening independent. Okay. I think I will define also the notion of white noise maybe in my third lecture, my formal informatically. But if you want a definition besides the picture, the white noise is a Gaussian field. So at every space you have Gaussian, a multivariate Gaussian, continuous multivariate Gaussian distribution. A Gaussian distribution is determined by its correlation function, and the correlation function of the Gauss of the white noise is delta. So here, for some reason, I put space and time. You can forget about the time, although we will deal with this, after the third week. The delta function is maybe people have seen this. This is a function which is everywhere zero, except that zero takes the value infinity, and still the is 1, is not 0. Right? If you have a continuous function which is everywhere 0, and then let's say at 0 takes the value 1, its integral will be 0. But the delta function, because it takes a huge infinite value at one point, its integral is 1. And this is a fundamental notion. It's called Dirac delta function in physics and everywhere in mathematics. So this infinity is really reflecting, is really quantifying the plus minus infinities that we have here. Okay. So this is a notion of independent random variables in the continuum. This would be a basis, as it would be as fundamental in the continuum and later on when we do stochastic analysis, as is the notion of a family of independent, identically distributed random variables. Okay. But then to functions which are in nature also have some more structure. So let's look, this will be the objective from maybe week 3 or maybe week 3. I'll give a seminar on week 3 where I'm going to discuss specifically about this model. And then maybe towards the end of week 3 and week 4, we'll be discussing this in more detail. So this is a picture of some other kind of random picture which is very spiky. And this picture on the right actually is what you see if you run inside here and you try to zoom out. So for the moment, don't bother about these two pictures, but keep in mind that and try to compare it with the previous picture of the white noise. So here we also see a spiky picture, but it's not so uniform, right? Because most structure that we would like to understand. So this is a picture of what is called the solution of the stochastic heat equation. And the stochastic heat equation is the equation that we see in the top. It has the part, the derivative in time equals 1/2 the Laplacian. If you just look at this equation, it would be the heat equation. But then you add a term, which is the white noise, so the picture that you saw in the previous slide, multiplying the solution. And then you try to solve this random equation. So this is an example of a stochastic partial differential equation. So, usually in advanced undergraduate or graduate level, then the notion of stochastic differential equation is then, this is when you have an ODE, an ordinary differential equation, you get it by noise, by the picture I was showing before. Now, this is again one-dimensional. It is if you flip a coin, okay, one-dimensional thing. But then, in nature, we want to understand things which are in many dimensions, in 2 dimensions or 3 dimensions. Or if you look at quantum field theory, I don't know how many dimensions they like to go to. And then you have the deterministic part, which is a heat equation, and then you prepare by a stochastic theory. This has a meaning, actually. In the case of the stochastic heat equation, you can think of this, you can give an interpretation of some population moving around, and multiplying randomly according to the inclusion that they find in places. So then you see how the population would increase. Okay? So maybe here there was no nutrition, so the population died out, and the population moved to places where there were good resources, and then they increased. Okay. I would like also to say a couple of simulations, just because the heat equation and the stochastic heat equation. So let's try to simulate the heat equation. So, okay, let's wait a bit. The flat plateau here is just because Mathematica has to truncate as a ceiling. But, if we very soon will become a picture of the Gaussian distribution, right? So the bell shape, so the heat. So if you start with an element of very spiky heat somewhere, if you put heat in the middle of the so the heat profile will start spreading out in this Gaussian way. So the temperature will start reducing and spread out everywhere. So it has this bell Gaussian shape, the heat profile. Okay? Now let's try to compare this picture with the stochastic heat equation. And so again, it starts with a single set at the origin, a delta function at the origin, but then to have a kind of variation profile, but it's much more rough. Okay? So the population starts spreading out, and then they start to find the locations where there is mutation. Of course, the population will not have moved all the way here. It will take some time to move here. But then you start thinking about the shape. The shape is much more rough. Okay, it's still not as rough as the white house, but it is still quite rough. Okay, and then if we let it run for some time, eventually, so this is still a bit slow now. So I want it to run for 1600 steps. So here we are still one quarter of the time, but eventually we start seeing these islands of spikes. Okay, so and then this structure which we would like to understand. Okay. Right. So the question is, what to develop a series of methods, starting from very basic, like advanced undergraduate or graduate probability level, that eventually will give us a set of tools, which will give us a set of tools which eventually will allow us even to understand this kind of continuing stochastic PDE problems, and playing using an interplay between continuous and discrete. Okay, so this interplay will be very useful. So that's a summary of the final goals of the class. But now, yes, okay, one more comment. So here you see this randomness. This is captured by what we call fluctuations, random fluctuations. So you have a model which doesn't have a nice deterministic smooth profile like the heat equation. It has lots of randomness. These are fluctuations. And I would like actually to start with very basic. What are the fluctuations? What is the central notion of fluctuations in random systems, which is the central limit theorem? So the plan for today will be actually to go to the fundamentals, what is the central limit theorem, but then also give a proof which is not usually seen in the typical undergraduate or graduate text. So this proof will actually allow us to develop and introduce a method which is called the Lindeberg principle and the Lindeberg method. This method actually has been very useful in many contexts in modern probability when you want to go outside the standard central limit theory. And this is something that actually was also used to construct these objects that we see here. So, today I will talk about the Lindeberg method. I will try to demonstrate the Lindeberg method through proving the central limit theorem. I would also like to introduce, and this may also speak also in the next lecture, another very powerful method to prove central limit theorem, which is the Stein's method. So I think this is a very useful toolbox that you can have. And this requires actually not much more than the expression and also some hard work. Okay, but not so many fancy tools. The standard way the typical central limit theory is through the characteristic functions. We're going to a Fourier transform. But this has two defects. The one is that actually it requires quite a bit of foundation, to develop the Fourier theory, to be able to say that, okay, if you can characterize a convergence of the Fourier series, then you can characterize the measures. And on the other hand, it's very restrictive, this method of characteristic functions. It only works in the case that doesn't apply in such kinds of situations. It works in the case when you have a sum of independent random variables. not at much more complicated functionals. And that's where the power of these alternative methods of the Lindeberg principle and the Stein method comes. That has been proved very useful in modern times when problems from statistical physics arise and we want to use probabilistic methods to understand fluctuations of complex statistical physics models. Right, okay, so just to wrap up the place, so today I'm going to introduce a Lindeberg principle, a Lindeberg method, and apply it to the Lindeberg central theorem, which is again for the sum of independent random variables. I would also like to discuss the Stein's method, so maybe we'll complete it today, or maybe complete it in the next lecture. Then in the next lecture, I would like to start going to more complicated functionals. So not just sums of independent random variables, but non-linear functionals of independent random variables. And then we'll see how we will have moved, and then gradually I want to move to stochastic PDEs and introduce some discrete models that allow actually to make these pixels and which also form the foundation for studying these models. Okay, any questions or requests about the program here? If not, then maybe that's all I wanted to show you on the screen, and then we'll go to the green screen. So maybe we can remove this. Start as it does not ever said. So let's see the so the principle says that okay, it's a that we can have still extreme so on, starting of independent. So this is simplified way of developers. Okay. So independent is what happens to it, what happens to it. So in fact, to see it as a so for me, developers say the way value x Nikolaos one, x value Nikolaos two. So when separate this. Or another thing about Warwick, should have functions so far so on. So if you have the expected value of the product of x example is equal to the product of the expected values of xi. Now, when we can decide that's why we say is bigger than A, is equal to the x2 is bigger than A, is equal to this. Okay? Okay, so let's assume that this is what simplicity. Sigma square. And then the same thing theorem. So that x1 plus x2 plus x7 minus n times the u divided by the sigma square. This is the solution. Okay. And yes, we actually what is a standard development? Standard density. So the expected value of f of the standard number of variables. Similarly, the neighborhood of f of x equal to negative x squared divided by okay, if you're talking about one-dimensional Gaussian distribution. And what does it mean to have this distribution? Well, so what does it mean that the family of variables is a z converges to z distribution for one which is bounded continuous function. We have the projected value of f is what because expected value is used as a universal logic in different things. So when we say expected values, we take values with respect to the distribution of set. This will converge to the expected value of f z. So the expected value of the average of f with respect to the distribution of z. Okay, so this is the formulation of the proposition. Okay. Of course, this is equivalent to the fact that the is less than A converges to the probability that Z is less than A. If you want to be more dynamic, you can search for A continuity point. So whatever this is, so let's not pay much attention. Okay. This will always be the case. Okay, so this is what the simple theorem. It's actually is not this stage formulation, but it's really saying if I give you some can we estimate how much the sum is? And this theorem is formulation telling the very simple thing that that's sum will be approximately n times the mean for each one variable plus square root times distribution, something that is equal and is number. Okay, so if I use the points 1,000 times, then I will see the four ways to is and half 1,000 divided by 2. But we will never understand 1,000 divided by 2. However, we will understand 1,000 divided by 5. Let's say 10. It's one allowable vocabulary at the moment. With okay, so this is the story to keep in mind. So, okay, so this is the fundamental theorem, and now we can discuss like how we extend into okay. So what if the assumption if I want to distribute it? Okay. So let's now state Lindeberg's. See again. With first of the following. So X and is a family of independent. Simplicity tests the first take spoken by Jhih-Huang to visit zero. And let's assume that the variance now, because it don't have a solution, they will not have necessarily the same variance sigma squared. So let's call the variance of x sigma n squared. So we will depend on let's also be the problem variance. So the total, yes, the total variance of the sum F squared. Okay. Because the number of variables are independent, the sum of the variance of the sum of independent variables is equal to the sum of the variances. So sigma 1 squared or sigma 2 squared is sigma 1 squared. Okay. So by what do you know what the sigma 1 squared is? Now, asks also for the following. So we take the expectation of factor square on the event that the factor absolute value is bigger than epsilon S. We sum, it's a and we divide by epsilon squared. So the condition asks that at least normalize to zero is equal to infinity. Okay. So this is why we actually go to what it is. So if we didn't have an indicator function here, then divided by the square, this sum will be over 1. Okay, because without the indicator function, we have the expected value of the square. Because of the change of the variance, so we need to figure the square. And as the square is a small sigma change. Okay. So this sum actually without this expectation without the indicator function is a variance of the fluctuations of each individual variable. But now we look at the fluctuations of the variables only in the state of equivalence. How big? Total standard deviation, the total fluctuation. Okay. So this is a total fluctuation. By fluctuation, we have the pieces I was showing before. Things being up and down. Okay. So the total fluctuation of the sum is not equivalent by the values, by large values. Of sense. Okay. In other words, this essentially is equivalent to saying, and this is something valuable if you allow to keep in mind. One single value is major contribution. Well, in other words, all values are which value. With values value. All values x j divided by z normalized. Because of all because the total fluctuation before is small. When we have central limits, and this of course is something you need to check situation here, in this theorem, happens to variables code. And then we can also consider compute the exercise. And the probability that the function x to less than or equal to 1 is bigger and from square. So exercise. So that this is well, this as epsilon goes, this is small. Okay, goes up zero. So small. So actually, that's what someone asks you. When do you have a simple theory? And actually, this is a principle which we see with number when we develop the present. When we have simple theory. In fact, actually, the simple theory it's just the simple situation where we have look at the random variables with some sort of variable. So here, the theorem says that each one has the value by is the relation of the constant distribution. Okay. So what the philosophical discussion was developing is that okay, here we have this intermediate theory. Once somebody asks, okay, what are all the situations that fit the theory? And in the consideration, and also become it says that we have simple theory for functionals within variables where no single variable is a major distribution. So if you related these variables, we have the singularity. If you variables, so you have collectively the contribution for the things. If I want to give for example that starts in next two, I wouldn't be so much because it's the variables that is what the variables will. Okay. So if you want, this is kind of the language that works better to have a simple theory. Simple theory. Okay. And that's actually one of the things, about what the means simple relationship to some conversions. Some conversions not something we will be discussing, but some conversions is relevant. We have some conversions. One is the value variables. It's much bigger than the all values. Okay. So that's what I want to have simple relations for some conversions. The value has any contribution to some conversions that the fluctuations are given by one variable, which is which will be bigger values. Okay. So this principle those times. So start and this is actually very beautiful idea. Okay. So remember this exactly. So the central theorem is is called temporal because it doesn't matter about this distribution. So variables of distribution that you give me such that no one has a larger distribution level from which one you have a system. But one variable for which the theorem kind of distribution. And this distribution is actually themselves to be worse themselves. Because the sum of constants is also goes with values, the sum of the balances. So first of all, is that CMP is trivial if I is a normal variable zero, and then of course, variance with the sigma and square. Let's call this psi. I standard process in loud it's slow goes. Okay, where is this? Well, of course, x1 plus xn. If I divide by the x, x1 plus xn is equal to distribution to standard. Okay, well, because it's the number of the process, so 1 plus xn is equal to values, which is the sum of all values. And we call the sum of the balances also squared. Okay, so when we divide by the sum of the standard deviation, then we will be getting standard deviation. Okay, so now you have a situation and then the idea is, okay, how much? So, but I want to have a simple theorem for this general level. So, then we can compare the case where you have rows and numbers. Now, that doesn't mean what you call it. Function expectation to convince the blocks in the brain into the x squared value that's what you plug up in. But we know that in this case, because this is just so this is equal. Everyone is into negative x squared. Okay. So if you consider that this difference converges to 0, by the fact that this is exactly what is approaching the block, then the limit of this sequence of expectations converges to the design operations integral. Okay. So the idea is to compare the two situations. Part of the comparison, we start with the telescoping. So, telescope. So it's so we just equal 1 to 1. Expected value. So I'm going to change gradually 1 by 1 variables x, variables psi. Okay. So you have so option plus x2 plus xn divided by plus n minus f of xi1 plus x2 plus xn divided by xn. So if the one return, and then we can go product plus expected value of f of xi1 plus x2 plus xn divided by xn minus minus x2 by xi2. Expected value of f of xi1 plus xi2, and then we have x plus xn values of xn. Okay. Now, subtracting these values, so we have it. So xi1 plus xi2 plus x3 plus so now we expect the value x3 by xi. Okay. So we would like to expected value of f outfits the first j minus 1 values of xi, and then I continue with x minus the expected value which is one variables up to and between the closed one, and then I will continue with x. So I wrote this compact summation from telescopic doing. So here. Actually, see, okay. So this telescope, this expression here, the functions that are from the rest of the expectation, this is the expectations. Expectations so of expected values that we then with respect to the x. This becomes one place at the jth location. So at the jth location, the j summing, the first term has a variable x, and the second term has a variable xi. Okay. If then the two terms will be the same, so someone just will take the zero. But if you don't expect this variables to be removed, if you expect this to be small, If you raise it from that side, you shouldn't be losing much. But that's why these metrics here. That's why every single variable has major contribution. So if I raise this, that's normal. But even if you prefer, it's as if it's normal because it's small, it's just the variable is small itself. So you would expect that this term is actually small. And the question is, it's small actually, but when you sum all these things, it's still involves to zero. So the variable that the case is small cumulatively. Okay, and that's the thing that to check. That's what we will see. Okay. So now I'm going to do the improvements. Okay. As I mentioned, has this inspiration. So I think mathematics has a balance. Okay, the one is that you have to have a result, and the other is that you have to work out. Okay, so for you should be you should propose okay. As I said, at this stage, is the physical thing is just table expansion. So we start with table expansion. Table expansion has precisely to do here. Okay. So we have the variable functional this without. So let's do the table expansion. So for this, we have to keep things stable here as stable as possible. And then we can use notation. Should we stop? You stop it because it was a thing.
Yeah, it's up to you. Again.
Yeah, I think that's a to stop. Okay. What's the questions
So far for the first part? No. So we'll just resume in 20 minutes. And there's a there's a tea break. Yeah.
So we stop at this point. And we saw that this Ascent goes to converge to zero. And then we will expand for function and this discrepancy. But let's introduce some notation first. So let's introduce this notation, which is we introduce the function fn. So let's introduce maybe, because I don't want to divide all these relations, so let's introduce omega in bxi divided by sn and psi in bxi I divided by sn. Okay. And then we also introduce the function fn of omega 1n and so on, omega nn to be f of omega 1n plus f of plus omega nn, right? So in this case, this will be maybe actually here want to be so maybe if I have a function, yes, little. So this is a function of real variables, not an array, just a function, multivariate function, and then we define this to be as f of x1 plus xn. Okay, so I define this function. So we are interested of a function of this form, f of the sum, let's say, of omegas and psi's. But when I want to do Taylor expansion, I want to view this function as a function of n variables. So that's why here I put fn of x1, x2, xn to be f of the sum. And this f is the best function that I'm taking here. The best function that I'm taking here. So on the last piece of notation, I'm going to lift the blackboard, is I'm calling h x. X is a vector determined by x1, x2, and so on. Again, these are variables, real variables, not random. Okay. H x sub n I of y. The function f of n, where all variables are x minus 1, and from x I plus 1 onwards are n, x, and the variable in between is y. Again, this is a preparation because I want to do Taylor expansion. And this time, this is the discrepancy that I have. So here is all the notation, it's a little bit. And then we can write the top sum as expected value of n of what? Of psi 1 n, psi j minus 1 n. And then I have omegas, omega, and this will be, I'll keep it in red because this will be the place where we will be doing the Taylor expansion. Minus expected value of f psi 1 comma psi j minus 1 n. And here I have xi j n. And then I'll continue with omegas. And if I go back to use this notation here, this will be the expected value of the function h and j, because the discrepancy will be a j. And before I have size, and before j I have size, and after j I have. Okay, so this is, yeah, okay, let me introduce this vector here. This notation, one more notation. So by xi omega j, I denote the vector xi 1, xi j minus 1, and then go to omega j plus 1. All the way to, okay. So this is a vector, it's the first j minus 1 components of psi, and the components from afterwards are omegas, but doesn't have either psi j or omega j. So in particular, this vector here will be independent. This is something that we will be using. Will be independent from both psi jm and omega jm. The j variable, either this is psi or this is omega. Okay, that will be something important that we will be using. The independence will be used through this. So far, we haven't said anything about independence, right? Or any kind of assumptions. Okay, so this function now I denote by HMJ of omega Jm minus expected value H that vector psi omega is empty with J of psi Jm. Expansion of this function around zero. So, okay, so for simplicity, I'm going to be creating this notation, this superscript here. This is just, but we keep in mind that the function h, if you take away the variables, function variables which are independent of the jth coordinate, but that's the thing that we need to keep in mind. So, Taylor expansion. So we expand around zero, so we have h and j at zero plus the first derivative. The first derivative with respect to this coordinate here of h at zero times omega Jm plus 1/2 the second derivative of h at zero, and then we get the square, the variable that we plug in inside, plus an error term. Okay. And the error term will depend on omega. This is just simple Taylor expansion, okay? The value of the function, let's say at y is equal to the function, the value of the function at zero, plus the first derivative of the function at zero times y, plus half the second derivative of the function at zero times y squared, plus the error, which will depend on and the error will have, so if I call it r of y, it has this precise integral formulation, 1/2 integral 0 to y, the third derivative of h evaluated at t, okay, times y minus t cubed squared, sorry, dt. Okay. So this is a precise error. If you Google Wikipedia Taylor expansion, you will find this problem. Now we can do the same thing for the second term. So I'll just copy what I had above, but instead of omega, I'm going to put psi. And now we would like to check the expectation of these things. Right? Then we would like, after we evaluate the expectation, to take the difference. So let's start seeing what happens with the expectation. So here, actually, we can look, right? So, and this expectation actually, with respect, okay, so the expectation, but this function here will depend on psi and the omegas, but without the jth coordinate on both of them. Okay. Now we hit with expectation the second term, but precisely because this function h will depend on x's and omegas, which do not include the jth coordinate. The two things will be independent, so the expectation will be into product. Okay. Same below, when I take the expectation of the whole thing, the expectation will be equal to the expectation of h times the expectation of psi. Okay. Precisely because the function h doesn't include the j coordinate. I take the expectation here, the second term in the Taylor expansion, again, the expectation will be into a product of the expectation of h times the expectation of omega. And below, will be the product of the expectation of h, the second derivative of h, times the expectation of psi squared. And then for the remainder, because it has this kind of, you cannot really do much here. So we leave it. Right? Because omega, so you cannot do anything. So, okay. But now we take the difference of the two things. Okay, so now we want to evaluate the difference of the first and the second line. Well, the first two terms are the same. They're exactly the same. This term here should be to 0. So the whole things are actually cancel out exactly. In this case, they're exactly 0. In other situations, you may not have them exactly 0. Okay. Actually, Lindeberg, there is a kind of a method of Lindeberg principle. You need to have first and second moments the same, and some control on the other term. The other term is how negligible is each one. Okay. Actually, keep this model because we will use it maybe when we look at the stochastic equation of the last lecture. First, or maybe also in my talk in week 3, you need to have matching first and second moments and some control on the error. So here, these two terms are identical because both of them are 0, but in principle, you didn't need to have 0 as long as this is mu and this is mu, they would cancel out each other. That's what happens here. So this term is equal in both situations, and the expectations, we have the assumption that is equal, they are equal. Okay, there will be sigma j squared divided by Sn squared. So these two are equal. So when you subtract, the two terms go away. So in order finally control the error, the difference between the two, to control the difference of the errors. And because you cannot do much, you just need to make sure that the error in expectation is small. Okay? And you need to quantify how small. You need to make it small enough so that when you sum total errors, you get something which is negligible. So here, so far, what we have used the independence, the very crucial way, because of this factorization. The independence is used crucially here. We have used that we have zero specific value. We have used it, we have specified the mean and the variance, but we still haven't used the Lindeberg condition. The Lindeberg condition will be used precisely to control the cumulative error. So let's see how this is going to be used. So let's have some manageable estimates on the error term, because we cannot do much with this. So in absolute value, we can have two estimates on the error. The one is 1/6 times the third derivative, the third derivative of f, okay, times y cubed in absolute value, And the second bound we have is the L infinity norm of the second derivative of f times y squared. So we have two bounds for some reason. So how do we apply this bound? These are not difficult to see. So the first bound, we just put absolute value, take the L infinity norm, the maximum, the third derivative of h, but the h is just f. Okay. So basically, the third derivative of h is just the third derivative of f. And once you pull out the maximum of the third derivative of h, or the third derivative of f, then you remain with the integral of y minus t squared, which gives you the y cube, one y cube. For the second, you first do integration by parts. So before putting absolute values inside, you do integration by parts. So you pull one derivative from h into y. So you will get minus a half the second derivative of h evaluated at 0, because when you put and then times times y squared. Okay. When you look at the bound t equal 1, this term will drop out, so it becomes 0. Plus, yes, minus 1/2 the integral between 0 and y, the second derivative of h evaluated at a. So when we hit y minus t squared, the square will cancel the 2. So then we will be getting y minus t dt. Maybe the way I wrote this would require a plus here. And now you put the absolute value, you take out the maximum second derivative of h, and then you integrate y minus t, which will give you another half y squared. So that's why putting the two terms together, you get this one. Well, because we have a different estimate, will be variable. So y can take either big values or you can take small values. When you take big values, it's better to have an estimated y squared. But when you take small values, it's better to have y cube, because higher powers of something small are smaller. Okay, so that's why we need to use the two different bounds depending on the variable that we put here is big or small. Okay, so let's try now to estimate the same, the cumulative error, the expected value, let's say, of the absolute value of r of omega jn. So the second, that's why we use Lindeberg condition. Second term can be used actually because you know psi is a Gaussian. You can even just do a Gaussian estimate. So we can break now this expectation. So we can round this from the estimate that I have by simplicity. So I'll put this tilde less than tilde times the expectation of what? Of the maximum of omega j cubed versus omega j squared. And then we will break this expectation into two parts. The one where omega j n in absolute value is bigger than epsilon, and one when omega j n in absolute value is less or equal to epsilon. When it's bigger than epsilon, we consider it to be big, so we'll be using the square root. when omega j is less than epsilon, we consider it small, so it's better to use a cubic bound. Now, right, so in the square bound for the moment, we leave it as it is. In the cube bound, well, that's exactly the good thing about using higher powers. We can take one power out. We can bound to direction. So we'll have epsilon times the expected value of omega j squared. And now we can direct the constraint. Right? So we can direct the constraint and we can get a bigger expectation because the square is positive, omega square is positive. So you just extend the integral without any constraint. Okay. So and bounded by epsilon, we left the other two powers, and then we direct the constraint so that we extend the integration and get something bigger. Okay. But now, and here is the sum, j equal 1 to n. But the sum of omega squared is equal to 1. Because the expected value of omega j squared is sigma j squared. We divide by Sn. So I remind you here. Omega jn squared is omega j squared divided by Sn squared. I take the expected value. So this is sigma j squared divided by Sn squared. And then when we take summation j equal 1 to n, but the numerator is just what we define as Sn squared. Okay. So this is equal to 1. So the second term, cumulatively, when we sum over all the j's, we just use this epsilon. And then we remain with the second term, with the first term. So j expected value omega jn squared and the set that omega j is bigger than epsilon. But then if I same way like in the previous blackboard. So what do I have? I have 1 over Sn squared times the expected value for omega j squared. And then I integrate the set where omega j is bigger than epsilon Sn, right? Because omega j is omega j divided by Sn. Plus epsilon. Okay. But as n goes to infinity, this term is exactly the Lindeberg condition. Well, yes, thank you. Thank you. Yes, yeah, thank you. Making is also the blackboard behind things. Yes. Because omega jn is defined as xj divided by Sn. So that's exactly the term that you can only control by the assumption. That's Lindeberg's condition. Basically controls is used to control the angle term. So the fact that no single variable has a major contribution leads to the fact that this Taylor expansion cumulatively converges to zero is negligible. So this is the idea of Lindeberg's principle. So now you can also ask about rates of convergence. So if you have some control on this arrow through this expansion here, then you can obtain some quantitative bounds in the order. Okay, but for this, some better estimate. So the Lindeberg's condition is not quantitative. It tells you that something goes to zero. Okay, but if for example you have finite third moments, you could actually manipulate this argument a bit to get a rate of convergence of 1 over square root n. We will see the rate of convergence a bit more in the Stein's method we will do, which is again, has a different starting idea, but this idea is also implemented by the parallel Taylor expansion. Whatever way we will also see the rates of convergence. Okay, so that's the Lindeberg principle. Any questions? That's a Lindeberg method. Okay. So another reason I decided to let me clean a bit and keep the important parts for the comment I want to make. Okay. So here you see there was also another reason why the sample f of the sample f of the sums as a multivariate function. Because this method can be extended and then we will extend to functionals of the random variables. So it doesn't need to be x1 plus x2 plus xn. You can have some general function f of x1, comma x2, comma x3, comma xn. And then you can still have stuff that so for example, you can ask, okay, I mean, the naive thing is that maybe this thing also satisfies this is the limit theorem. This is not a linear function. It's not the sum of the independent random variables, for example, right? Or you can have more complicated functions. That's important. You can have more complicated linear functionals. So you can have some function phi of I1, I2, Ik, xi1, xi2, xik, and then this function may be dependent. And then you can take all kind of collections of i's. Then situations like this also satisfy the limit theorem, like those far from obvious, right? There is something that we will discuss next time, which is called the fourth limit theorem. This is a very impressive theorem, very surprising if you see it at first. If you try to understand it a bit more, it becomes less surprising, but that's the deal with mathematics, right? So calculus now is trivial, but when Newton discovered it, it was a breakthrough, right? So the first limit theorem says that if you have multilinear forms like this, you can still have a simple limit theorem. If the first moment, you take the fourth power of this, you compute the expectation. If the first moment converges to 3, then you have a central limit theorem. So, and such kind of central limit theorems are very important for statistical mechanics. And you look at the Zygouras systems, or when you come to statistics, to have some tests which are non-linear functionals. of the random variables. Okay. So the interest nowadays is when you have linear functions, complicated linear functions, whether it comes from statistical mechanics or statistics, or maybe other problems in mathematical analysis. So the Lindeberg principle is a robust method, actually, to compare distributions of nonlinear functions of random variables. And when situations have central limit theorem, then for, let's say, Gaussians, the first limit theorem was functions of Gaussian variables. But then you can use Lindeberg principle to extend if you have nonlinear functionals of independent random variables with, let's say, enough moments, so that the form of Lindeberg idea that one will have major contribution is satisfied, then you can have universality, so you can prove central limit theorems for such kind of wide class of variables. So that's also one reason I wanted to write f of the sum as a nonlinear function, because then you can just forget about the specific form. And as long as you can preserve the independence, that's something that is important. When you start having derivatives, you can preserve some independence so that you can do this breaking. That's why it's good to have multilinear. Then you can have, let's say, central limit theorem, or you can compare distributions random variables. So this brings us to the end of the Lindeberg principles. So are there any questions about the protocol, the method, the details, or where this is all heading to? Okay. Okay. So we will see this, precisely, actually, we will see this step by step change. It's also called the Lindeberg exchange principle. Really, we start with the stochastic equation. The pixels is the very fun pixels that I showed you. It follows the same idea. And then we also try to give you some other examples from dissolving systems, statistical mechanics of dissolving systems. Okay, so this wraps up the first part of my lectures. Actually, I think with the range of classes, so maybe in general, we should stop. I know this is dangerous as well, options record it, but I will say it in any case, we should stop moving central limit theorem with characteristic functions. Still restrictive with Lindeberg principle. Those times methods that I'm going to describe. So for the moment here, I was following some notes for the graduate class of doing at Warwick the past couple of years. I can ask the administration to follow the notes to you with the precise pages where these are covered. Okay. So Stein's method. So Stein's method, again, starts from a very simple idea, or maybe a fact that it can be dismissed, but that's actually the significance of not dismissing simple things. So the fact is the following. So let's be a standard normal variable. Then we have the Gaussian integration by parts. So if f is bounded function with, let's say, has one derivative Actually, the only thing we need is that it has a derivative. It's absolutely integrable, such that I'm going to put the conditions in a minute. Okay, maybe such that the expectation of z absolute value, which is actually the integral of little z into the negative little z squared divided by 2. If this is finite, so if the derivative of f is integrable, absolutely integrable with respect to the Gaussian measure, so it doesn't have super Gaussian growth, then the expected value of z f of z is equal to the expected value of f prime of z. Okay. Right. Well, again, this is just a simple Gaussian integration parts. Okay. Because you recognize z times Gaussian K1 as a derivative of the Gaussian K1. So you have f times the derivative of the Gaussian K1. So you do integration by parts, you pass the derivative from the Gaussian K1 to f, and you get this part again. So one thing that is very important is that actually this is a characterizing property of the normal variable. So the normal is the variable which will satisfy this functional equation for a sufficiently large class of functions f. Yes, yeah. Actually, no, this is not Stein's equation. Stein's equation is closely related, but it will come in very soon. Yes. So as we told you, some lecture notes should have covered, which you can find on the website. So in my lecture notes, the reference is given, so you can look. Actually, we gave the whole course many years ago with Stein's methods and applications. And this is very interesting because the first few lectures is about the basic of Stein's methods, but then again, the scope of these methods to prove simple theorems are very wide. So then he goes to spin classes, he goes to random matrices, he goes to many other topics. Okay, so what's the idea of Stein's method? Well, as we said above, so suppose that a family of random variables Wn, if the was a simple ring, x1 plus x2 plus xn divided by square root n, converges in distribution to some standard normal random variable. So this means that for all functions z, which are, let's say, bounded continuous, we should have the expected value of GWN minus the expected value of G of Z raises to 0. That's, the first part of the tailor, what it means, convergent distribution. Or equivalently, because I want to follow functions, you can have the supreme over G bounded functions, and this difference going to 0. Okay. So now that's where the Stein's equation will come. So Stein's equation So it's the following calculation. So given a function g, suppose that you want to find the function f such that f g of x minus the Gaussian average. So this is just the integral of g against the Gaussian kernel, the Gaussian density, is equal to f prime of x minus x f of x. Okay? Suppose that for every function g that you give me, I can find the solution f. And maybe f belongs to some, so there exists f in some other class, let's call it DQI. Okay? So such that for every g, let's say, in bounded continuous functions, there exists an f in some other class. Other class means there will be some properties that the solution, if a solution exists, the solution will have some properties dictated by this equation. But suppose that given g, you can solve this equation for f, and of course for all x. So you can solve this differential equation. F prime minus x f of x is equal to this function. Okay. Then plug in f equals the Wn. Okay. And then you have g of Wn minus the expected value of g of z. Right? The expected value here with respect to Gaussian. So sorry, the simple probability we have this problem is ambiguous. So here expectation is with respect to this random variable, which is expectation with respect to Gaussian. Here expectations with respect to this random variable, which is expectation with respect to whatever distribution Wn has. Okay? So P of W minus expected value of z with respect to y is equal f prime of Wn minus Wn f of Wn. And then you take the expectation with respect to Wn. So, of course, this term here is a constant, so it will be affected by the expectation. And then on the right hand side, we have the expectation of this functional of W. Now, if W was itself Gaussian, of course, the left hand side will be zero, but also the right hand side will be zero because of the Gaussian integration by powers. So, if you want to prove that Wn is asymptotically Gaussian, you want to prove that the left-hand side converges to zero as n goes to infinity. So it will be enough to show that the right-hand side converges to zero as n goes to infinity. So if I now look at the supremum of the g's which are bound continuous, so for every g that is bound continuous, assuming I can solve the equation, I'll have a function f which will be in class. So maybe here we take the supremum over the class that f belongs to of the right hand side. So, okay. So if you can prove that there is a sufficiently large class of functions, the right hand side goes to zero. Then you have also that the left hand side goes to zero, which is the central limit theorem that you want to prove. Okay. And now the problem becomes what kind of properties we need to have here for the function f, or you can have for the function f. And then basically building the calculus. So basically you do Taylor expansions the same way, similar to what we did before. You have to compute these derivatives. Okay, we will keep it through an example. Now, another thing that the time method is very powerful is that this part becomes basically a real calculus part. So often Stein's method can give error estimates. Okay. So you can get the first considered, but then often it gives the size for the error. That's why Stein's method is also quite powerful because it allows for error estimates. So this is the idea that I'd like to implement. Yeah. This one. No, no. Which one? This? Not actually, because if you want to condense distribution, you want for every x let's say is bounded continuous, this thing goes to 0. You give me 0. Then I go find it which satisfies this. And that would be the f that I put here. Okay, so this f that I put here will depend on the g. Okay. Yes. Mm-hmm. It's not a, well, that's actually part of what we need to be a bit careful. That's why this place here. Okay. So given we have this, let's say, functional distance, distributional distance, and we will see that actually maybe this cosmographic distance may not be good, maybe Wasserstein absolutely better. Okay, then I will introduce what is a Wasserstein distance, where you indicate the supreme overall Lipschitz functions. And then if you look at the supreme overall Lipschitz functions, if you look here at the Lipschitz function, if you look at the class of f, such that for each Lipschitz function you have this solution, the f will satisfy some other properties, and this property will be important when we try to do the calculus here. So, yes. Yes. It can be noted that yes, the example that I will show you, it will not be sharp the example that I'm showing, but in general, with Stein's method, you get sharp rates of convergence. Maybe Chile knows this things very well. So you can use the picture here. Okay. Yeah, that's why I'm lifting it. Yes. Yeah. Yeah, there are some, yes. So Stein's method is also the Stein's chain Stein method. So chain actually was for the Gaussian convergence. And then this has been developed over the years very much. It's a very big chain Stein method community. I cannot say I know the whole scope of what are distributions, but the Gaussian and the Gaussian are the two paradigms, and then you can look at the values. Yeah. So Stein Gaussian, and then Chan, who was a student of Stein, did it for Gaussian, and then you need to find characterizing operator. Okay. So the characterizing operator is something like a generator, right? The characterizing operator for Gaussians is this derivative minus x multiplication. Okay. Gaussian will have its own characterizing equation. So you need to find the characterizing equation of your distribution, and then you need to solve the corresponding Chern-Stein equation. And then you need to do the calculus. Yes. Okay, thanks for the questions and the interaction. So I think maybe I can erase this. Okay, I think we don't have too much time. What I'm going to do is I'm going to produce some distances. I will in fact actually the Wasserstein distance that we will be working with. And yeah, okay, and then some properties of that Stein's equation. So what I wrote here is a Kolmogorov distance because it's a vector convergence distance. Take the supreme over energies which are bound to continuous. The Wasserstein distance between two distributions, let's call it mu, is the supreme of the integral, the supreme of the integral of f mu minus f du, where now f is Lipschitz 1. And then an exercise of the Wasserstein distance methods is that this can also be given via coupling. So you take all possible joint value values x and y, such that x has maximum distribution given by y has maximum distribution given by mu, and you take the expected value of the absolute value of the difference between x and y. Okay. Now, this corresponds to this expression here, where, let's say, W would have distribution mu, and Z would have distribution mu, and then the supreme is not taken overall by continuous function, but it's taken overall Lipschitz functions, Lipschitz 1 functions. So, we will be looking at this convergence central limit theorem with Wasserstein distance. So we will be replacing this by Lipschitz 1 functions. And then there is, of course, a relation between Lipschitz Wasserstein distance and Kolmogorov distance. So that's where you lose the estimate that I will be showing you. And then the question is, okay, so if you solve here this equation for Lipschitz, what class of functions do you get? What is the big value? Okay. So that's a proposition I'm going to write, and we will stop here. And then we'll start from this point next time. So there is this lemma, I think this is also called Stein's lemma. It says the following, so suppose that, so let's say G, which is from a real function, which is bounded. Okay. Then there exists f, which is absolutely continuous. Absolutely continuous does that have derivative understandable, such that Stein's equation has a solution. F prime of f minus x f of x is equal to g of x minus the Gaussian integral of g. And now that's where the conditions come. So actually, it's part of a lemma that's I'm not going to skip and then go to the case where it's Lipschitz functions, Lipschitz 1 functions. So if this Lipschitz 1 function, this of f, which is absolutely continuous and solves this equation, and has the following properties. So the L infinity of f is bounded by the L infinity of G prime. The L infinity of f prime is bounded by square root 2 over pi the L infinity of G prime. And the second derivative of f is bounded by twice the maximum first derivative of G. So everything basically the function of the solution. There's a solution, it's derivative, and second derivative can be controlled by the only factor of G prime. And why do we have F prime and F double prime? Well, because we will do Taylor expansion. Then we will go second order Taylor expansion. So we need F prime, F double prime. So we need to have some appropriate control here. Right. So let's keep this. So I was not planning to but I'll give you some hints. So the idea is actually to write a solution to this equation. Each way has its benefits in terms of getting these estimates. The first way is the standard, second differential equations. So we multiply this out by e to the negative x, and then this is a complete differential. So then a first form of the solution is just e to the x squared divided by 2 integral x. And I think I may have forgotten something. I think I taught this class a couple of years, and when I was looking at this morning, I found a few typos, but my students didn't follow. So let's pose these questions whether they have actually read them. So I think here there is minus y squared divided by 2, which is missing. Okay, so again, side by e to the negative x squared divided by 2. The left hand side will be a complete differential, and then we just integrate. The second form, which is more distinct, and here yes, you can get some kind of easy bounds, but actually, yes. Yes, actually, I'm going to double check whether this is G or G prime. My formula says that this should be G. Okay, so this is another typo I need to mark here. Okay, the second formula of the solution, which is much more interesting, is the following. So f of x is integral between 0 and 1. This, of course, shows you the power of probability. 1 over square root times 1 minus 2, expected value with respect to the Gauss standard normal variable z, times g of square root t x, x is the real variable that appears here, plus square root 1 minus t, the standard normal variable z, and integrate between 0 and 1. Okay, that's totally crazy, right? Solution. So this is something actually used very much in statistics, because let's say if x was not a real number, but it was a variable, a standard variable, then the whole thing here would be a standard variable. So this is the, if you want, the convex decomposition of Gaussian variables here, the square root t, square root 1 minus t. Okay. And I know that there is a course in spin glasses, and I'm sure you have seen lots of these things in spin glasses used. Okay. Right, and then also this one, you can get some this estimate. So I'm not going to go through these estimates, how we get them. This is the calculus, level calculus, based on these formulas. Yeah, the proofs are also in chat of this Loxonos. I haven't included them here. Okay, so that's Stein's lemma, that's a idea of Stein's method. So next, We start actually by the Lindeberg, actually the central limit theorem with the Steins method, and then we will solve also the rate of convergence here. So we will solve that the Wasserstein basis between the x1 plus x2 plus xn divided by n from the normal will actually be bounded by some constant, which depends on also the first derivative of f divided by the first derivative of g, which is divided by square root of n. Okay, so we get this one of the square root of speed of convergence of the Gaussian. Okay, so next we will finish Stein's lemma. We finish the application of Stein's lemma. Maybe I'll point another example that you can help us in any research project. This example is known. So have a random graph, and you put edges at random. What is the number of flow records? That's also symbolizes simple theorem. Okay, but that's one fact you can get in the Stein's method is maybe as easy as what we will do with the standard simple limit theorem, and then discuss function, which is something we will be using. I will discuss, but not because I will discuss, but not the Lindeberg principle for multilinear polynomials. The proof is a more careful analysis of what we did in the linear case. And then I will also motivate these Lindeberg theorems with some couple of examples from statistical mechanics, from resolving systems. And then this will produce us to some discrete models, which we then will use to construct the stochastic equation. Okay, so thanks. I'll stop here. I hope to see you next week.